Hello and welcome. So this is the last week of this course. Today is the first class of this last week. So in the last class we were learning about different molecules and their normal modes and their symmetries. So using group theory, how we can find out about the characteristics of the normal modes. And there we found a very interesting thing. So we discussed about three different molecules belonging to three different point group symmetries. So we had planar CO3 to minus, which was planar having D3H point group. We had trans planar into F2 belonging to C2H point group, and we also looked at a pyramidal NH3 belonging to C3V point groups. Now, when we were discussing about the this normal modes and particularly on the context of vibrational spectroscopy, so two spectroscopy we were discussing which gives us information about vibrational transitions. They are infrared spectroscopy and Raman spectroscopy. So in these three molecules, we figured out that which of the normal modes are Raman active and which are IR active. So we figured out that for this first case, we have normal modes which are both IR active and Raman active. In the last case, that is for C3V point group, we figured out that there are modes, normal modes, which are both IR active and Raman active. Now, in this particular case, we found that no normal modes that is both IR active and Raman active. Right. So, if we look at some other molecules, for example, SF6, we will also see the same behavior as we see in case of trans into F2, which is a transplanar configuration. Now, the common between this particular molecule or this point group or the point group to which SF6 belongs to, or say for example benzene belongs to, all of them are centrosymmetric. Okay. So centrosymmetric means all of them has inversion center, while all the other type of molecule that we discussed, they do not have center of inversion. So from our experience so far, in last two classes, we see the molecules which has the center of inversion behave completely differently compared to any other molecule which are devoid of center of inversion. So is it a general rule that for centrosymmetric molecule no Raman active mode will be infrared active and vice versa, while for other type of molecules having no inversion center, no such rule will be applicable? So is it a general rule or not? Let's figure that out. So let's take in general. So is centrosymmetric special case here? In this context, so let's figure out. So for showing IR spectra for any normal mode, the normal mode should transform as the irreducible representations for which any one of the Cartesian coordinate forms a basis of. So for any mode to show infrared activity, the normal mode should have the should transform as the irreducible representation that has either x or y or z as basis set. It may be more than one also. So, this is the condition, because we have seen the transition moment integral is like psi say v I, which corresponds to the 0th vibrational level. Instead of I can also write 0, no problem in that, and then you have either x or y or z, and you have this. Okay. So, in this case, since this forms the basis for totally symmetric IR, or this transform as the totally symmetric IR of the particular point group, then this particular normal mode must transform as the irreducible representation to which x form the basis of. So, therefore, the irreducible representation, or if I say the symmetry of this and this, must be same, correct. So, for a molecule which has center of inversion, meaning I have an operation I, what will be the fate of this x, y and z? So, when I operates on either x or y or z, we get either minus x or minus y or minus z, right. So, that means this x, y, z, they are anti-symmetric with respect to inversion. So, when I say anti-symmetric with inversion, that means these must have a U type of symmetry, correct. So, U type symmetry or U type irreducible representation, I can say. So, it will belong to something like AU or BU or EU, that kind of symmetry. Therefore, in order to show IR activity, this normal mode also belong to U type of irreducible representation, correct. So, in general, for a molecule having center of symmetry, if I want to if one particular normal mode has to be observed, transition for a normal mode has to be observed using infrared spectroscopy, then that particular normal mode must be of U symmetry. Perfect. Now, let us look at what happens in case of Raman spectroscopy. So, for showing Raman scattering, I have to have the normal mode which is being excited to level V equals to 1 from V equals to 0, that must have the same symmetry as that of the any of these polarizability tensors components, which is something like x square or y square, z square or xy or xz and so on. Now, if I consider again a centrosymmetric molecule, so if I operate I on any of these binary functions, so say xz, so both x and z, they will be inverted, but overall it will give me back the same thing. So, that means this is true for any of these functions which form the components of the polarizability tensors. So, therefore, these functions are of G type, meaning that in order to show a Raman transition, a Raman spectra for any particular vibration transition, the involved normal mode must belong to G type of symmetry. Now, in case of Raman, I need a mode which has G type of symmetry, while for showing IR spectra, the normal mode must be U type of, must have the U type of symmetry. Now, for a centrosymmetric molecule, one IR, one irreducible representation cannot have both U and G type of symmetry, correct? Similarly, I can say for the particular wave function that we are talking about, a particular normal mode we are talking about. So, one normal mode cannot have both U and G type of symmetry, that is clear. Therefore, those particular normal modes having U type of symmetry will show only infrared spectra, while those which those normal modes having G type of symmetry, or which transform as the infrared the irreducible representation belonging to G type, they will show only Raman spectra when they are excited to level 1. So, I can easily see for a centrosymmetric molecule, no normal mode can have a transition which is possible to be seen both in IR spectroscopy as well as Raman spectroscopy. And this particular this is kind of an exclusion, right. So, this particular thing is called mutual exclusion. So, rule of mutual exclusion. So, many of you must have heard about this rule of mutual exclusion, but here is actually the real logic behind this particular rule of mutual exclusion. Now, you just think about any other molecule where you do not have the inversion symmetry. What happens in that case? In that case, you do not have this U type or G type irreducible representation present, right. So, there this situation does not arise at all, because you do not have inversion symmetry in those cases. So, this formation of having this XYZ coordinates as anti-symmetric with respect to inversion, this at all does not occur. So, therefore, I do not have to think about having such exclusion. So, this kind of mutual exclusion is possible only in case of centrosymmetric molecule. So, this is indeed a special case. All right. So, in vibrational spectroscopy part, we will limit ourselves up to this point. One can try to look at some more advanced topics, like we have been restricting ourselves to the study of fundamental transitions, but one can look at various other things like overtone transitions, their corresponding selection rules or combination bands, and one particular interesting things that is extremely important in case of vibrational spectroscopy, which is known as Fermi resonance. But we will not go through these topics in this particular lecture series. But if anyone is interested in that those topics in advanced level, so a standard textbook like what we suggested at the beginning of this course, they have this topic discussed very well. So, one can go through this one. So, now we will move on to the application of group theory in other type of spectroscopies. So, mostly we will deal with the electronic spectroscopy. So, while discussing about vibrational level, what we were discussing? We were discussing about the particular particular type of motion, like known as normal mode of vibration, and each normal modes for any given molecule, they will constitute a particular state, and these states are the vibrational states. So, if I talk about this molecular oscillation, so this V is equal to 0, V is equal to 1, V is equal to 2, and so on, they will be contained in a so called potential well, right. So, if we restrict ourselves to simple harmonic oscillator, then these are different vibrational level. So, you can keep on going up, right. and we were discussing about how will be the nature of this particular type of motion for one particular normal mode, and what will be the symmetry, and then finding how I can talk about the allowedness or disallowedness of one transition between this level, right. So, we were dealing with this vibrational transitions, and we dealt with two spectroscopic technique. One is by using the infrared light as such, and another one was to excite the molecule to some place which we call generally a virtual state, where there is no real state, and which comes back to one of these vibrational level. So, we have a probe for the gap between two vibrational levels. So, that was about vibrational spectroscopy. Now, this about the simple harmonic oscillator, but in real life you have a potential well which is depicted by something like Morse potential, and you have the vibrational levels here also, and so on, right. Now, this each well, it constitute the electronic state of a molecule, right. So, these individual things are vibrational states, and this well gives you the electronic state. So, you can easily figure out that one electronic state contains both vibrational and obviously the rotational levels. So, rotational levels will be in between. So, if we have a situation when this is my ground electronic state and there are some other electronic state at higher energy which also has their own vibrational levels, then I can think about taking a molecule here, from here to this upper electronic state by giving some form of energy, preferably light, and this transition is called electronic transition. So, suppose this is my ground electronic state and this is my excited electronic state. So, a transition from here to here will definitely involve the transition of transition between different rotational and vibrational states within the electronic states. Now, in general, when we look at ensemble level spectra involving the transition between two electronic states, this rotational, fine rotational transitions are blurred. Even in most of the cases, vibrational lines also will be blurred, but within a limit of temperature, that is, if you cool down the system quite a bit, then I can see the vibrational lines and even some cases rotational lines as well. Now, in our discussion, we will not worry about the rotational level here or rotational transitions. Vibrational transitions we have looked at already. Their selection rules also we have looked at, but in the context of electronic transition, where the vibrational transition is also involved, we will look at the vibrations in a bit different way. So, what are the things that we should look at when I try to deal with an electronic transition? So, here we will try to see how the knowledge of symmetry and group theory can help us getting an idea about the selection rules of the electronic transition, the transition moments, the band intensities. Okay, all these things how can we get from our knowledge of group theory and symmetry. So, that is what we will look at. So, let us start from the very basic things which will lead us to the selection rules. So, finally, our aim is to get the selection rule for transition moment, for the band intensities, and also we will learn about something called Frank-Condon principle. All right. So, like here I showed one arrow, right, from one vibrational state in the ground electronic state to the upper one of the vibrational states of the upper electronic state. Now, can I draw the arrow just like that, or there is certain rules? Okay. So, those things we will learn, and we will also see how we can use this group theory to get information about those aspects. So, in general, the probability of any electronic transition is proportional to the square of the transition moment integral, right. So, if I say the transition moment integral as, say, any electronic state overall, if I am thinking about, and say I write psi prime for the excited state and psi as the ground electronic state, then this is my transition moment, right? And this transition moment integral, if it is 0, then there is no transition allowed. If this is non-zero, then the transition is allowed. Okay, that much we have learned so far, right? And it is true for anything and everything, any transition that we are discussing with. Okay, so depending on the situation, my operator may be different. In case of like Raman, we have seen that this is a polarizability tensor component. Now, when we talk about the electronics transition, okay, so there I have the vibrational states also involved, right. In case of pure vibrational spectroscopy, when we were looking at last week, so we wrote a very similar kind of thing, and there we did not explicitly differentiate with anything else, because we knew that when we are talking about vibration, all we are trying to do is looking at how two nuclei, that means two nuclei are bonded, and how this bond is executing a motion, keeping the center of mass fixed. And then we were probing all these motions, their transition probabilities and all these things. So, the coordinate that we looked at, that was the nuclear coordinate, correct, and that is still there here. So, here since we have electronic state, also vibrational state, so we will explicitly look at either it's a electronic coordinate or it's a vibrational coordinate, right. Now, I can write this operator mu, the overall dipole moment operator, as a sum of nuclear and electronic component, and I can separate them, because this nuclear motion and the electronic motion, their speed is quite different. So, I can easily separate them out, right. So, if I do that, then I can rewrite this aim as and also if I can do this, then I can do the same thing for the overall wave function. So, this wave function is essentially the product of the individual wave functions for electronic, spin and nuclear motion. Okay. So, I am talking about the electronic spin here. So, therefore, I can write this psi prime, or in general psi, as psi ES, E stands for electronic and S stands for spin, and psi N, or I can also write psi V, so that you can easily see that this stands for the vibrational wave functions, right. So, essentially they stands for one particular normal mode. So, once I explicitly write like this and using this operator form, I can rewrite this as, so here we have to remember that this should be complex conjugate, right. So I write, so instead of writing the prime on this psi, I will write it on this E and S, okay. And then you have psi V, and V also here it is in excited state, so I will have V prime having the complex conjugate, and then you have mu ES, sorry, mu E and mu N, right, and then you have the ground state part. So you have psi ES multiplied by psi V, integration over all the space. So this we can do. Now we can separate these integrals. So let's start from here. So I can have psi E prime S prime psi V prime, and I can have it over mu E, and you have the left over part, that mu ES mu V d tau plus the other integral using this mu N coordinate, right. So I have the same thing, mu E prime S prime, sorry, psi E prime S prime, psi V prime, and then I have this mu N and the ground state part. Okay. So here this electron and spin that I can, this electronic motion and vibrational motion, I can decouple them, because one depends on the electronic coordinate, so, and the other one, the vibration, which depends on nuclear coordinate, has nothing to do with this mu E operator. So I can have this integral, that is nu V prime nu V prime mu E and nu psi V d tau multiplied by the rest of the part, that is E prime S prime over mu E psi ES d tau, plus here also similarly I have this psi E prime S prime psi E S d tau multiplied by psi of P prime mu N psi V d tau. So I have total 4 integrals here, right. So here if I look at this part is equal to 0, right. Why is it so? Because this psi ES or psi E prime S prime, they are the wave function for the electronic states, right, and these wave functions should be orthogonal to each other. Okay. So they are normalized as well as orthogonal. So this particular integral of two orthogonal functions will give me 0. So therefore this part is completely 0. So I am left with only this part. So here you look at this particular quantity, which gives me the this is an overlap integral of two wave functions, two vibrational wave functions, right. So now one can ask that, okay, I have this particular integral having a value 0 because of the orthogonality, then why not this case? This also should be 0. But actually there, I mean, it need not be 0. Why? Because I am having a transition between two vibrational levels, right, from here to somewhere, but these vibrational levels, they belong to two different electronic states. Therefore, it is not necessary that these psi v and psi v prime will be orthogonal, right. So therefore, that not necessarily 0. So this term survives. So therefore, I have my overall aim equals to this part, that is psi v prime psi v d tau multiplied by psi e prime s prime mu electronic psi e s d tau. And this particular part that we were just talking about, this is known as Franck-Condon factor. All right. So I can take this product of integral, which is now my transition moment integral, and we can split them even further. So this electronic part and the spin part, that I can split further. So therefore, what I can write is as a two different integral. So maybe I will write here. So at last, when I consider electronic motion and the spin part separately, then I have psi v prime. At some places we miss this complex conjugate part, but you should correct it. D tau multiplied by d tau, and you have so multiplied by psi s prime and psi s d tau. So we ultimately got three integrals, the product of three integrals, as my transition moment integral. Now if any of this integral is 0, then overall the transition is forbidden. That I can say at this moment, right? Now this is a Franck-Condon factor that decides that from which vibrational state of the ground electronic state to which vibrational level of the excited state the electron will make the transition. This part is the electronic transition purely, and this is the spin transition. Now this particular integral is the basis of spin selection rule. So this particular part is the basis of spin selection rule. And this integral is the basis for electronic selection rule, or selection rule for electronic transition. Right. So this is the most general form, but the specific selection rules which will born out of this general form when we use the group theoretical knowledge and expand this a little further. So that we will do in the following classes. Thank you very much for your attention.